Today we're going to be talking about how to find the maximum volume of a rectangular box which has been inscribed in a sphere when that sphere has radius r. And the first thing we need to do with this multivariable applied optimization problem is to start writing down what we know. First of all, we know, or we should know at least, that the equation of a sphere is x squared plus y squared plus z squared is equal to r squared. And this should look familiar to our single variable equation for the circle where we had x squared plus y squared is equal to r squared. Now we're talking about a sphere in 3 dimensions. We just add this z squared component. So this is the equation of the sphere with radius r. Notice though that we're looking to maximize the volume of the rectangular box. So we know right away that we're going to need an equation for the volume of the box because that's going to be the equation that we're looking to optimize. Well, if you imagine a sphere centered at the origin and a box inscribed in that sphere, so let's go ahead and draw a picture of what that might look like quickly. If we have a sphere like this and it's centered at the origin, and I'm not going to do a very good job drawing this in 3D, but let's say we have this sphere like so, and its center is at the origin, and we're inscribing a rectangular box inside of it like this. And I won't draw this box in 3D, but essentially here the box is also centered at the origin. What we know is that the box has width 2x because the distance from the origin out to the edge of the box this way is just some distance x. So the width of the entire box would be 2x. We would double it to get the width of the entire box. In the same way, we don't know how tall the box is yet, but we know that we have to go from the origin out to some distance y to get to the edge of the box this way. And if we go this way, we just double it, and the height of the box is 2y. And in the same way, the depth of the box is 2z. So we want to say that the volume of the box, we'll say v sub b, is going to be equal to 2x times 2y times 2z. That's going to be the volume of our box. If we simplify this, we get, of course, 8x, y, z, like that. Now remember, since this volume equation is the equation that we want to optimize, right? We're looking to find the maximum volume, so we know we need to optimize our volume equation. We need to get this equation down into 2 variables at most. Well, the way that we're going to do that is by eliminating our z variable, leaving only x and y. And if we use this equation here and solve it for z, we get z squared is equal to r squared minus x squared minus y squared. Taking the square root of both sides, we get z equals square root r squared minus x squared minus y squared, like this. Now we have a value for z that we can plug into our volume equation. So our volume equation becomes 8xy, and here's where we plug in for z, square root r squared minus x squared minus y squared. And now we have a volume equation that's in terms of 2 variables only, keeping in mind that the radius is not a variable because the radius is a constant. We've been told that the radius is r. We basically treat that as a constant, so our only variables that are remaining in this volume equation are x and y. Now, in order to optimize this equation so that we can find maximum volume, we're going to need to take first-order partial derivatives of our volume equation and then find critical points. So let's go ahead and take the partial derivative of our volume equation with respect to x. In order to do that, we're going to need to use product rule to take this derivative. We'll treat 8xy as one function and square root r squared minus x squared minus y squared as our second function. So using product rule, we first take the derivative of 8xy with respect to x. That's going to be 8y. And we multiply by this second function without touching it. So we get square root r squared minus x squared minus y squared. Then we add to that the opposite situation. This time we're going to leave 8xy alone, so plus 8xy, and now we need to take the derivative of square root r squared minus x squared minus y squared. Well, let's pretend that instead of square root here, we have r squared minus x squared minus y squared raised to the 1/2 power, right, which is the same thing as the square root. We can use product rule to take this derivative. So when we do that, we bring that 1/2 exponent down in front. It becomes the coefficient. So 1/2 times r squared minus x squared minus y squared. We subtract 1 from the exponent to get the new exponent. 1/2 minus 1 is a negative 1/2, so negative 1/2. But then we have to multiply by the derivative of our inside function. Essentially here we've used chain rule, and we've treated the outside function as just some value raised to the 1/2, and we used power rule to bring that 1/2 down in front. But we ignored the inside function, and now we need to multiply by the derivative of this inside r squared minus x squared minus y squared. The derivative of this with respect to x, remember we're treating r as a constant, and the derivative of any constant is 0, so that's going to go away. With respect to x, negative x squared becomes a negative 2x. We multiply this by negative 2x, and the negative y squared drops away because we treat y as a constant when we take the partial derivative with respect to x. Now we just need to simplify this equation, so the partial derivative of volume with respect to x here, we're going to get 8y times square root r squared minus x squared minus y squared. And then here we have this negative 2x. We notice that the 2 is going to cancel here with this 2 in the denominator, so we just have this negative sign. We'll pull the negative out in front, and we'll get minus 8x squared y. We pull this x in front to combine them with this x right here to get x squared, so negative 8x squared y. And now all we have left is this r squared minus x squared minus y squared to the negative 1/2. Well, remember that the negative 1/2 we can turn into a positive 1/2 by moving this whole value to the denominator. So we move it to the denominator, and we have this quantity raised to the positive 1/2, which is the same as the square root here of r squared minus x squared minus y squared. So we just turn it back into a square root by moving it to the denominator. Now here we want to combine this into one fraction. We want to find a common denominator. So multiplying this first term here by square root r squared minus x squared minus y squared in order to find a common denominator, we get that value, that square root, in the denominator here, and our square root in the numerator disappears here, and essentially we're just left with quantity r squared minus x squared minus y squared. Now just to combine these fractions, we have the partial derivative of our volume equation with respect to x. We're going to pull an 8y out in front, so we have this 8y here, multiplied by, here we have r squared minus x squared minus y squared. We have an 8y over here multiplied by a negative x squared. So if we pull that negative x squared into this quantity here, we get r squared minus 2x squared minus y squared, all divided by our square root common denominator, r squared minus x squared minus y squared square root. Now we're also going to need the partial derivative of our volume equation with respect to y. In order to do that, you'd follow the exact same process as you did to find the partial derivative with respect to x. You'd use product rule, treating these as two separate functions, and you'd just take the partial derivatives with respect to y. So instead of, for example, getting 8y here, we'd end up with 8x. We'd keep this whole square root here. This 8xy would stay because we don't take the derivative there. And here you'd have the same thing, 1/2 times quantity r squared minus x squared minus y squared to the negative 1/2. And here you would just multiply by negative 2y. Then you just cancel, you do your simplification, you find your common denominator, and your partial derivative of the volume equation with respect to y would give you 8x when you factored out an 8x. 8x times r squared minus x squared minus 2y squared, all divided by the common denominator you found of r squared minus x squared minus y squared square root, like this. So now that we've got our partial derivatives, what we need to do is realize that we can use them to find critical points. Remember, critical points occur where the partial derivatives are equal to 0. So how do we get these to equal 0? Well, if we make the denominator equal to 0, then these fractions are going to be undefined. So we're not really interested in those values. We're only interested in values where the numerator is equal to 0, which would make this whole fraction, this whole rational function, 0. But here, if we make y equal to 0, that does us no good, because remember, we're dealing with real dimensions. We have a volume equation equal to 2x times 2y times 2z, where x, y, and z are real dimensions. Remember, the value of y was literally this three-dimensional value, or this value in three-dimensional space right here. So y can't be 0, because then we wouldn't have a rectangular box. We need this to be some positive number. So we can't set y equal to 0, we can't set x equal to to 0. The only value we can set equal to 0 that's going to make these partial derivatives equal to 0 are these values here, this quantity r squared minus 2x squared minus y squared in the partial derivative with respect to x, and this corresponding quantity here in the partial derivative with respect to y. So here, if we say r squared minus 2x squared minus y squared is equal to 0, remember r squared is a constant, so we can solve this for r squared. We'll add negative 2x squared and negative y squared to both sides. We'll end up with 2x squared plus y squared is equal to r squared. This equation here, r squared minus x squared minus 2y squared, we'd set that equal to 0 and solve for r squared doing the same thing. We'd get x squared plus 2y squared is equal to r squared. Now, if we treat this as a system here of simultaneous equations, we can go ahead and multiply the second equation by 2. We multiply through the left and right hand side by 2. When we do that, notice we'll get this 2x squared here to match up so we can subtract the equations from each other and cancel out an x. So when we multiply through by 2, we're going to get 2 here, we're going to get 4 as the new coefficient on y squared, and we're going to get 2r squared. Then when we go ahead and subtract this second equation from the first one, right here, the result that we get, we'll get our 2x squared minus 2x squared, that's going to go away and become 0. We'll get y squared minus 4y squared, which is a negative 3y squared, and then we'll get r squared minus 2r squared, which is a negative r squared, negative r squared. If we multiply both sides by negative 1, we get 3y squared is equal to r squared. Dividing both sides by 3, we get y squared is equal to r squared over 3, and then taking the square root of both sides to solve for y, we get y is equal to positive or negative r over root 3, but keep in mind that we can't have the negative value, negative r over root 3, because that would give us a negative value for y, and again, we're talking about a real distance for y. If we had a negative value for y, our rectangular box would not exist. So the only value for y that works is y equals positive r over root 3. Now to find a value for x in terms of r, all we need to do is plug in this value for y to one of these equations. So let's go ahead and plug it into this equation here. What we'll get is 2x squared plus, here instead of y squared, we'll plug in this value, r over root 3 squared, because we square it right here, is going to give us r squared over 3 equal to r squared on the right-hand side. If we find the common denominator and treat the right-hand side as 3r squared over 3, and then we subtract r squared over 3 from both sides, we get 2x squared is equal to 2r squared all divided by 3. Dividing both sides by 2, we would get x is equal to r squared over 3, and then taking the square root of both sides, we get x is equal to positive or negative r over root 3, but again, we can only take the positive value because x is a positive distance, a real value in three-dimensional space. So now we have x equals r over 3 and y equals r over 3. That's a critical point that we would suggest would give a maximum volume of the rectangular box. Because there is only one critical point, we can assume that that is the critical point that gives maximum volume. And now, because the question asked for maximum volume, we just need to plug this critical point back into our volume equation to find volume in terms of the radius r. So we're going to be plugging the critical point r over root 3, r over root 3 into this volume equation here to find volume. When we plug in that point, we'll get volume of our box is going to be 8 times r over root 3 times r over root 3, and then we multiply by square root of r squared minus r over root 3 squared minus r over root 3 squared like this, and we put this all under our square root sign. Now we just need to simplify. So out in front here, we're going to get 8r squared over 3, because our root 3 times root 3 will give us a positive 3 like that. Inside of our square root here, we'll have square root r squared minus, when we square these quantities, we get r squared over 3 minus r squared over 3. If we find a common denominator underneath our square root sign, we'll call this 3r squared over 3, like that, multiplying by 3 over 3. That's going to give us 8r squared over 3, and inside our square root, we have 3 minus 1, which is going to give us a 1r squared over 3, so we have r squared over 3 like this. If we take the square root there, what we end up with is 8r squared over 3 times r over root 3, and when we combine those, we get a final answer of 8r cubed over 3 root 3, which is the maximum volume of this rectangular box inscribed in a sphere when that sphere has a radius of r.